Chapter 5, Magnetism and Matter. In last lecture we have discussed that one solenoid is equivalent to a bar magnet. Solenoid is equivalent to a bar magnet. Solenoid means it is a helical coil having current flowing from it. Okay, yes, in chapter number 4 we have obtained one equation, if you remember. K, torque acting on current carrying coil in uniform magnetic field. In uniform magnetic field is tau is equal to m cross b. Is m cross b. Yes, we have obtained this equation. Okay, where what is m? M is magnetic moment. M is magnetic moment. Yes or no? Yes, it is. Okay, and yes, in last chapter and also in yesterday's theory, we have obtained one relation. K, current carrying coil or solenoid, it behaves as, or it is equivalent to bar magnet. It is equivalent to bar magnet. Okay, current carrying coil is equivalent to bar magnet. Bar magnet means I can also write magnetic dipole. Magnetic dipole. Okay. So what is meaning of this? What is meaning of this? Okay. If we place magnetic needle in uniform magnetic field, in uniform magnetic field, torque acting on it, tau is equal to, it is m cross b, like this. If it is uniform magnetic field B, if it is uniform magnetic field B, in this magnetic field, if I place a needle like this, okay, if I place a needle like this, then yes, see, it is north pole, that is south pole. Okay, so magnetic moment, it is in this direction. Magnetic moment is in this direction. So yes, there is some angle between magnetic moment and magnetic field. That is theta. So yes, in uniform magnetic field, torque acting on it, tau is equal to it is m cross b, means I can write its magnitude. Tau is equal to it is mb sine theta, where theta is angle between m and b. Theta is angle between m and b. Yes or no? And yes, you know that this torque rotates dipole until it aligns in the direction of magnetic field. Okay, this torque aligns needle. This torque rotates needle until it aligns in direction of magnetic field. Clear about this? So yes, I think you know this topic. Yes, this topic is similar to electric dipole in electric field. Okay, yes, we know that when electric dipole is placed in uniform electric field, torque is acting on it. And yes, that torque rotates dipole until it aligns in direction of electric field. So here similarly, if we place a magnetic needle in uniform magnetic field, torque acting on it, tau is equal to m cross b, tau is equal to mb sin theta, theta is angle between m and b, and this torque rotates needle until it aligns in the direction of magnetic field. Clear about this? Clear about this? Okay. Now, once that dipole is in direction of magnetic field, once this dipole is in direction of magnetic field like this needle is like this, needle is like this. Okay. So yes, magnetic field is in this direction, magnetic moment also it is in this direction. Magnetic moment is from south pole towards north. Okay, so yes, here what is angle between them? Theta is equal to 0. So yes, here what is torque acting? It is 0. Means it is in equilibrium. It is in equilibrium. Needle is in equilibrium. Clear about this? So what is behavior of magnetic dipole in magnetic field? If dipole is placed at any angle, if dipole is placed at any angle, torque is acting on it, and due to torque it is performing rotational motion until it aligns in the direction of magnetic field. Once it is in direction of magnetic field, theta is equal to 0, torque is equal to 0. Now it is in equilibrium condition. Now it is in equilibrium condition. And we know that from equilibrium condition, it do not move by itself. It do not move by itself. If I want to rotate, okay, let needle or dipole, needle is rotated through angle theta, If needle is rotated through angle theta, or displaced by angle theta, like this. See, if it is uniform electric field, okay, it is equilibrium condition. From this equilibrium condition, if needle is rotated at angle theta like this, it is M and here it is P. Okay, so yes, displacement of needle, it is in this direction. It is displaced in this direction. Clear about this? But we know that if we displace dipole in this direction, yes, this torque tau is equal to M cross P. This torque tau is equal to M cross P is acting on dipole such that it tries to make this dipole in direction of magnetic field. Means this torque is acting in this direction. Okay, this torque is acting in this direction, and due to this torque, this needle will try to regain its original condition back, its original situation back, its original position back. So yes, this torque is called restoring torque. This torque is called restoring torque. Yes. Okay. One another example. If I move this chalk, it will fall freely due to gravitational force in downward direction. If I have one needle like this, it will rotate until it aligns in the direction of magnetic field. Will this chalk move by itself in upward direction? No. Yes or no? Because gravitational force is acting in downward direction. Will this needle move in this direction by itself? No, because restoring force is acting in opposite direction. Yes or no? Yes, it is. So yes, we have to displace this dipole against this restoring torque. So when you displace, that needle is rotated through angle theta or is displaced by angle theta, restoring torque acting on dipole. Restoring torque acting on dipole. How to write restoring torque acting on dipole? See how to write restoring torque acting on dipole. Yes, here it is. Restoring torque acting on dipole. It is tau is equal to minus md sine theta. Now you may think, sir, why minus sign? Because here restoring torque is in opposite direction of displacement. Here restoring torque is in opposite direction of displacement. So here restoring torque is in opposite direction is in opposite direction of displacement. Clear about this? So that's why there is minus sign. That's why there is minus sign. Now if displacement is small, for small displacement, how to write? I can write this equation as tau is equal to minus mv theta. Now remember in the chapter number 7, rotational motion tau is equal to I into alpha is equal to minus mv theta. Where what is I? I is called moment of inertia. Okay, so yes, I alpha is equal to minus mv theta. Now I alpha means d square theta upon dt square is equal to minus mv theta. Therefore, d square theta upon dt square is equal to minus mv upon I theta. D square theta upon dt square is equal to minus mv upon I theta. Clear about this? Okay. Now, remember again 11. Simple harmonic motion. D square y upon dt square minus omega 0 square y. Second order differential equation for simple harmonic motion. Why? It is linear displacement. Omega, yes, omega it is angular frequency, and y is displacement. See, y is linear displacement, t is time, angular frequency and displacement. You can compare this equation with rotational motion. Yes, we have compared linear displacement y, angular displacement theta, So if you compare these two equations, see, theta, angular displacement, linear displacement, time, minus, theta, angular displacement, linear displacement. So yes, I can say this mv upon I is equal to omega 0 square. Yes or no? Yes, it is. And see, it is equation for simple harmonic motion. So yes, it performs simple harmonic motion. Clear about this? And for this simple harmonic motion, what is mv upon I? It is omega 0 square. It is mv upon I. So what is omega 0? It is under root mv upon I. Omega, yes, what is omega? 2 pi f. So yes, I can write it is 2 pi f is equal to under root. Here it is mv upon I. Any doubt? If you make f as subject, then what is equation of f? F is equal to 1 upon 2 pi under root mv upon I. And yes, time period t is equal to 1 upon f. So it is 2 pi under root I upon mv. Yes, you have to remember these equations. Clear about this? So yes, remember when dipole is in equilibrium condition, from equilibrium condition, if it is displaced, restoring torque is acting on it, which will try to bring this dipole again in equilibrium condition. Restoring torque, tau is equal to minus mv sin theta. For small angular displacement, sin theta is nearly equal to theta. So yes, here it is theta. Tau, I alpha d square theta upon dt square. It is equation of simple harmonic motion. We have to compare 11th chapter number 14, simple harmonic motion. Okay, so omega 0 square is equal to mv upon I. Omega 0, equation of frequency and equation of periodic time. You have to remember. Clear about this? So yes, it is again one important theory, and yes, it is similar to chapter number 1. Clear about this? Now, potential energy of magnetic dipole in uniform magnetic field. Yes, potential energy of magnetic dipole in uniform magnetic field. Yes, we know that if magnetic needle in a uniform magnetic field is in equilibrium condition, is in equilibrium condition. Magnetic moment, it is in this direction. And if we want to rotate, or displace that needle at some angle theta, yes, obviously against restoring force we have to do some work. This job will not move by itself in upward direction. I have to do that work, and that work is stored as potential energy. Yes, you know concept of potential energy: gravitational potential energy, elastic potential energy, electrostatic potential energy. Here it is potential energy of magnetic dipole in uniform magnetic field. Yes, when dipole is placed like this, it is in equilibrium condition. Okay, so see how to write. If we want to displace dipole from equilibrium condition, work is done, and that work is stored as potential energy. So see how to write. Yes, work is equal to potential energy. So yes, U is equal to, or still suppose W is equal to. Yes, you know what is integration, what is equation of work. For linear motion, you know equation of work. That is work W is equal to is integration f dx. Work W is equal to is integration f dx. For rotational motion, what is equation of work? W is equal to integration tau d theta. For linear motion, force is responsible. For rotational motion, torque is responsible. Linear displacement dx, angular displacement d theta. I want to rotate this dipole. Initially it is in this direction, means theta is equal to 0, and here I want to write theta is equal to theta. So what is limit? It is from 0 to theta. Clear about this? And yes, we know that this work done is stored as potential energy. So therefore U is equal to integration tau means it is mb sin theta d theta. M, magnetic moment constant. B, magnetic field constant. Limit is from 0 to theta. Chalo, M, B constant out of integration. What is integration? 0 to theta sin theta d theta. We know that integration of sin theta is cos theta. So yes, it is MB minus cos theta. Limit is from 0 to theta. So here it is MB. First of all, minus cos, upper limit, minus cos 0. Clear about this? Minus cos 0. Clear about this? Okay. So yes, here it is equilibrium condition when theta is equal to 0. Here in this condition, it is angle theta. Okay. If we do not put limit, then we will get one general equation. That is, if I do not consider this limit, then I can simply write that W is equal to, U is equal to, it is minus MB cos theta is equal to, here it is minus M dot B. U is equal to, here it is minus M dot B. Remember equation of electric dipole in electric field. What is equation of potential energy? U is equal to minus P dot. So yes, it is one general equation. U is equal to minus M dot B. U is equal to minus M dot B. Where theta is angle between M and B. Theta is angle between M and B. Now I will consider two cases. See, case 1. Here it is case 1. See about case 1. U is equal to minus mp. Why it is dot product? M, magnetic moment, vector quantity. B, vector quantity. But U, potential energy, is scalar quantity. So yes, there is dot product between M and P. So U is equal to, it is minus M dot P. Now case 1. Uniform electric field in this direction. Needle in this direction. Magnetic moment in this direction. Theta is equal to 0. So U is equal to, it is minus mb cos 0. Cos 0 is equal to 1. So it is minus mb. Means minimum potential energy. Minimum potential energy. And minimum potential energy, it means it is most stable condition. It is most stable condition that we have already discussed in chapter number 1. This whole theory is from chapter number 1 and 2. Okay. Now case 2. Case 2. When magnetic field, it is in this direction. B. Needle is placed like this. The magnetic moment is in opposite direction. Then what is theta? Theta is equal to, it is 180. So U is equal to minus mb cos 180. Cos 180, it is minus 1. So it will become mb. Means maximum potential energy. And maximum potential energy means it is called most unstable condition. Most unstable condition. Clear about this? Now see, this equation of potential energy, case 1, case 2, most stable condition, most unstable condition. Now, see here, why I have erased this limit? Because I will make one general equation. Yes, here you can put limit 0 to theta, 0 to theta, 0 to theta, 0 to theta. You will get your right answer. But I want to make one general equation. How? See, here it is. If it is uniform magnetic field, B, initially dipole is placed like this. At angle theta. Okay, and then it is placed at some another angle. If it is rotated at some other angle theta, then what is work? Then yes, work is equal to, it is integration theta 1 to theta 2 tau d theta is equal to integration theta 1 to theta 2 mb sin theta d theta is equal to mb constant. What is integration of sin theta? Minus cos theta. Limit is from theta 1 to theta 2. So is equal to, it is mb here minus cos theta 2 minus it will become plus cos theta 1. Minus it will become plus cos theta 1. So here yes I can write it is minus mb. Here it is minus mb. If you take this minus common, then it is cos theta 2 minus cos theta 1. Minus cos theta 2 minus cos theta 1. Clear about this? So yes, such equation we have already discussed in chapter number 1 and 2. In chapter number 1 and clear about this? Any doubt? Okay, so yes, you have to remember this theta 1 to theta 2 and the constant. Sin theta, its integration is minus cos theta. Put upper limit minus cos theta. Here there is always negative sign. So okay, it will become minus. Clear about this? Any doubt? Okay, so yes, it is about when magnetic needle, magnetic dipole, bar magnet is placed in uniform magnetic field, then what happens? Okay, take care about this integration tau and b sin theta's integration minus cos theta to upper limit minus cos theta also will become positive. If I am taking minus common, then it will become positive and it will become negative. Clear about this? Okay, so yes, you have to remember this all equations for dipole in uniform magnetic field.